Welcome to Module 4 of Digital Forensic Essentials. And in Module 4, we're going to be looking at data acquisition and duplication. In Module 4, we're going to look at several different areas. Number 1, understanding data acquisition fundamentals. Number 2, the different types of data acquisition. Number 3, the format for data acquisition. And probably what I would say is the core of this module is we're going to look at the data acquisition methodology. So let's get started. The first thing we want to look at in this module is understanding some of the fundamentals of data acquisition. So with data acquisition, what we're trying to do is use an established method to extract ESI. ESI is electronically stored information, digital information, information that is somewhere stored. Now, the reason we say electronically stored is because there are so many different methods to store information. Could be storage media, could be on the computer. We want to gain insight into the crime that took place or an incident that has taken place. And so we want to gather that data, verify the accuracy of that data, and there needs to be a process. And this process needs to be able to be auditable, reproducible, and acceptable to the court. There are two major types of acquisition we want to look at. Number 1 is live acquisition, and the other is dead or static acquisition. With live acquisition, we have a system that is currently powered on, whereas with static acquisition, the system is turned off. With live acquisition, we collect that volatile data from a live system. And so we need to make sure that we get the timeline of the incident, when it occurred in relation to other factors of the incident, and possibly the users that are involved. If we look at logon information, time information, we can correlate that. And then live acquisition can be followed then by static or dead acquisition, where we shut down the machine, remove the disk, and acquire all of that forensic data by creating an image of that disk. So what type of data can we get from live acquisition? We both have system and network data that we can acquire through live acquisition. And the system data is the configuration, the running state, date and time, uptime. How long has it been operating? Was it recently rebooted? That's going to be our system uptime. Running processes, who's currently logged in to the system, any DLLs that are currently up and being used, and shared libraries and swap files and temp files, all of that. System data and more, by the way, this is just a summary of some of this stuff, can be acquired through live acquisition. And also network data. What current routing tables, ARP cache, DNS cache, network configuration, network connections, and more networking data can be acquired during live acquisition. It's very important to deal with the order of volatility. So if you're doing a live acquisition, you're dealing with volatile data. The system is turned on. There is memory stored, information stored in various locations around that computer system. So let's have a look at the order of volatility. And this is defined by RFC 3227, which you can look up if you want, and it gives you a lot more details. And as defined with RFC 3227, number 1, the most possible, the most volatile data is in registers and cache. So like for instance, in the registers on the motherboard near the CPU or in the CPU, L1, L2, L3 cache, those are very volatile storage areas. After that, it's a routing table, process table, kernel stats, and memory. And so that memory would be RAM. That routing table is stored in RAM. Same with the process and kernel statistics. We can pull that information out, but they change pretty quickly. And they can also be easily lost. And then after that is temporary system files. And those are usually stored on hard drive, on the hard disk, on the SSD. And the problem with those is often they will get erased by processes or scripts or be modified through time. The next is disk or other storage media. So your hard drive, your SSD, and it's much less volatile than any of these others. So it's number 4 on the level of volatility. And we move from there to number 5, remote logging and monitoring data that's relative to the system in question. So for instance, you might have a SIM system or some type of log storage or monitoring system that gathers information from that system that's way less volatile than even the disk drive. And then from there, the physical configuration and the network topology. So what's actually plugged into the motherboard? Where is the system located? What is the switching and routing topology of the network? And then lastly is media archival. So if I have a backup tape that has a couple of terabytes of data on it and it's in an archive somewhere off-site, that can sit for years. And so that's the least volatile of all data. So that's our data volatility hierarchy. But guess what we need to do? We need to work with that because we need to acquire that data. So let's talk about dead acquisition. Dead acquisition is when the system is powered off. So we get it from DVD drives, flash drives, smartphones, things like that. So like for instance, you can collect emails and examine the email headers and Word documents and the contents and the metadata and web activity and spreadsheets. Remember Slack space? We were talking about how data can be hidden in Slack space on a hard drive, unallocated drive space, and various deleted files. And a lot of deleted files can actually be very easily undeleted or with some effort undeleted. Rules of thumb that you need to think about for data acquisition. Number 1, don't work on the original, because if you accidentally make a change even one bit of that data, you can make that data completely inadmissible. So you want to create a bit stream, a logical image of that suspect drive and work on that, not the original. So you always want 2 or more copies of the media. The first one is the working copy. You're going to use that first one for your analysis, for your forensic analysis of that information and of that scene. And the other one is going to be a control copy, a library. And this is going to be stored and being used for disclosure purposes. So for instance, if you have to hand over this information because of a court case, you want that to be available. You want to use clean media to store the copy. So not something with any information already written on it. And you want to create copies of the original media. And then you want to hash the original media and hash your copy to verify that not 0 or 1 has changed in your copy and that it is 100% like the original. Now, if you run your hash and you find that the hash is different, then you need to run your copy again and then run the hash again. This brings us to the different types of data acquisition. All right, so the types of data acquisition, we have logical and sparse. Let's talk about logical. It's logical to start there. So logical acquisition allows you, the investigator, to capture only selected files and file types. We're looking for stuff that's important to the case. So for instance, we're investigating email. So we're going to specifically target Outlook files, OST files, PST files, or we have a RAID server. And by the way, RAID is a way that we make resilient and redundant data on a disk drive. If you're not familiar with RAID, a redundant array of independent or inexpensive disks. And so you are investigating that. Someone says, hey, I think we had an intrusion, or this is part of your investigation. And so you're only looking at RAID stuff. All right, in that case, it's a logical acquisition. The other type of data acquisition would be a sparse type of acquisition. So these are the first two. There are more. And this is similar to the logical, but we also have fragments of unallocated data. We're talking about those sparse files that we look for, or try to get those deleted files. And so this is when the entire drive isn't required, but we want to get a look back into some of those deleted files. Also, we can bit stream. Bit streaming is a bit-by-bit copy of the drive. And we clone that entire drive, all clusters, all sectors, which allows us to go find stuff that's deleted. So we don't just want to get the data that the disk drive has mapped in the GPT or the MBR, but rather we want to get all the sparse files and everything. That's why we need every 1, every 0 on that entire disk to be copied, and that's a bit stream. We could do bit stream disk to image, or we could do bit stream disk to disk, and let's talk about that. So the most common way is to do the disk to image, bit stream disk to image. And so we do a bit-by-bit replica of the drive, and we create an image file of that drive. This image file is very versatile because I can use it, mount it to different types of virtual, even physical systems, and review the data that I've collected. ProDiscover, Encase, FTK, the Sleuth, X-Ways, forensics, so many different tools that you can use to create a bitstream disk to image file. The next type is a bitstream disk to disk. And disk to image copying is not possible sometimes. So yeah, this is the way we most likely do it, but sometimes you cannot. Why? Because the drive is so old that the imaging software doesn't even recognize it. Or you need to recover credentials used for websites and user accounts. And so both of these are reasons why we might want to do a disk to image. And so what we do is we create a disk to disk, not disk to image, copy of that media. And what we do is we adjust the target, not the source, because we don't want to touch that source. We adjust the target disk's geometry because everything has to match. Head, cylinder, track configuration has to be the same as the suspect drive. And that way we can map 1-to-1 from the suspect drive to the disk that we're copying it to. And so we can use Encase, Tableau, Forensic Imager, and others to do a bitstream disk to disk. All right, let's have a look at the data acquisition format. What we want to do is determine the data acquisition format. So let's start with the raw format. The raw format, what does it do? It's raw. That means it's at the lowest level. It's bit by bit. And we can usually obtain this in the Linux DD command. I mentioned DD earlier. It stands for carbon copy. And you remember why, right? They already had CC allocated to that. A very nice tool in Linux. It's fast. It mirrors the data. It has minor read errors, very minor read errors on the source drive. Those are ignored, which is nice. So also it is read by most of the forensic tools. So they make use of DD, but it has disadvantages. It requires the same amount of storage as the original media. So if the original media was a 2 terabyte drive, then you need 2 terabytes of storage because of that raw formatting. Tools, which are mostly open source, might actually fail to recognize or collect those bad sectors, the marginal sectors. We need those because we need to examine those in our forensic process. So if we don't get those, that's a problem. So DD, even though it's well used, integrated with many types of forensics tools, has good advantages. Sometimes the disadvantages outweigh the advantages. Then there are proprietary formats. So we have commercial forensics tools that reach in to that suspect disk and save the image file, but it's going to be in their own formats. So there are some really cool features for some of these commercial tools with proprietary formats. We have the option to compress it. We have the option to save it on different media. We can split it into multiple segments. So if you have a system with a 20 terabyte drive and you want it to store it on Blu-ray, and you can have a stack of Blu-rays and still have integrity. You can incorporate the metadata into large files, and so the time of acquisition, hash values. So there's a lot you can do, but one major disadvantage is if you create the image using one of these tools, you may not be able to use it with any other tools. So if you use XYZ tool, it's proprietary, you may have to keep using XYZ tool and never export that to any other tool. So be careful when you do that. All right, also we need to next determine, in determining the data acquisition format, we can use the advanced forensic format, which is an open source acquisition format that has no size limit for your disk to image files, option to compress. This is often for the advanced forensic format, AFF, the best way to go because it allocates space to record metadata. It's simple in design, multiple computing platforms and operating systems, self-authentication. It's going to be using that AFM or AFD image file. So very nice format. All right, further, in determining the data acquisition format, we have several things to think about with the Advanced Forensic Framework 4, or AFF4. With AFF4, we were just talking about AFF, and AFF4 gives us a redesign, and it's a revision of the original AFF for large disk images, but it's faster. It reduces the time, especially in storing larger amounts of data. So the basic types of AFF4 are object volume streams and graphs. And so they're universally referenced actually through a URL, which is actually really nice. We extract the information, allows storage of that disk image data in one or more places while the information about the data is stored elsewhere. So that's that metadata. And then number 4, it stores more kinds of organized information in the evidence file, and it offers a unified data model naming scheme in this case. And this is why you'll find AFF4 in use for data acquisition more than most of these formats. All right, so let's have a look at the methodology that we use for data acquisition. The data acquisition methodology, and we're going to start with deciding what we're going to do. So let's say you arrive on the scene of an investigation, you have a laptop or a desktop or some type of device, you've determined the type of disk it's using. So what am I going to do? I'm going to figure that out, and then I'm going to choose the appropriate tool. Then I want to sanitize the target media. This is where we're going to store the image. It needs to be completely sanitized, right? So now we have to decide what path we're going to pursue. If the computer is turned on, then it's a volatile data collection. And then after we've completed that 100%, then we turn off the computer and we go to removing that hard disk and write protecting it, making sure that nothing else can be written to it. And only then do we acquire the non-volatile data. We need to make sure and plan for contingency. We'll talk about that. And then validate that data acquisition. So let's focus in, first of all, on step number 1. So in step number 1, we need to determine the data acquisition method. What are we going to use? It really depends on what we find when we start the investigation. We're going to be presented with the size and the time and whether or not we can actually retain that suspect drive or not? Can I take it with me or not? And so we have the logical sparse layer at the application. We have the file system layer, partition volume layer, and the disk image that we might be able to obtain. An example of step one, in the case of the original evidence, that original evidence drive needs to be returned to the owner. In case that needs to happen, as in the case of a discovery demand for a civil litigation case, check with the requester. So who is it that made the request? Probably somebody in the, like a lawyer or a supervisor. Find out whether the logical acquisition of the disk is acceptable. If not, you may have to go back to the requester. So it's very important to figure out what's going on and what access you have and what you need to do before you finish a step one. And so you may need to acquire only the data that's intended to be acquired. You may not even be able to make an entire disk image. So it's very important to talk with the supervisor, lawyer, or whoever it is who's requesting it. Step number 2, select the data acquisition tool. So we need to have the right tool, right? So we don't use a hammer for everything in the toolbox, so we need to find what tool we need for it based upon the technique, based upon what type of image we need and what's going on. So the tool needs to make sure not to change anything in the original source. It should log any I/O errors that occur and in readable form, including the type of the error, location of the error. The tool needs to have the ability to pass scientific and peer review. Results must be repeatable and verifiable if a third party is necessary. So in other words, anybody and everybody who makes use of this tool should get the exact same results. The tool should alert the user if the source is larger than the destination. I've seen this happen before a few times where you're in the middle of a copy and then it just fails and the error is not enough space on the receiving side. It's like, couldn't you have shown me or told me that I didn't have enough space before I started? And sometimes you can corrupt the entire process and have to start again from scratch. So it's very good if it alerts you that the source is bigger than the destination. So let's say the source is a 10 terabyte drive and your destination is a 5 terabyte drive. And you just happen to grab the wrong one off the shelf, or the storage area doesn't have that much space. Whatever it is, when you start the tool, it should tell you that there is not enough space to store so that you don't get halfway through and get an error. The tool should create a bitstream copy of the original content when there are no errors in accessing this source media. And the tool should create a qualified bitstream copy. Qualified bitstream copy is defined by duplicate, except in identified areas of the bitstream. So it's going to be a really good duplicate. When I/O errors occur while accessing the media, so we want to make sure to have a qualified bitstream copy. These mandatory requirements in the selection of the data acquisition tool. Step number 3, sanitize the target media. So you must properly sanitize the target media in order to have, if there's any prior data residing on it, before it's used for forensic data. Now, you might think, hey, what I'm going to do is I'm always going to use a brand new out-of-the-box resource. But even those sometimes have manufacturer information on it. So you need to sanitize it either way. So post-investigation, at the end of this, then, you're going to need to dispose of the media following standards to mitigate the risk of unauthorized disclosure of information. The media that you sanitized and then filled with image and image data, that image data that you acquired from the customer might have some PII or credit card numbers or employee information on it. And we want to make sure after using it that we destroy it, right? So we want to follow some standards for sanitizing media. There's the Russian standard, which is Ghost, P, etc., the German, and then American standards, and there's good old NIST, and I'm not going to go through all of these, but yeah, there are a lot of them. I like the DoD standard quite a lot. So either one of these can be used by your organization to make sure that you appropriately sanitize and then dispose of systems, the data in those systems. All right, so once we've sanitized the media, it's ready, we can acquire the volatile data. And so remember, volatile data is when the system is turned on. So that is right here. Previously we were seeing, we're right here at the top of the right-hand side, acquire the volatile data. So let's see what we need to do to make that happen. So if we turn off the computer, that volatile data is lost. And these are running processes, processes, logged on users, DLLs, clipboard contents, open files, registries, stuff like that. So we want to do that from this Windows machine. There's a really nice tool called Belkasoft. What is Belkasoft? Belkasoft is a live RAM capture forensic tool that allows you to extract the entire contents of a computer's volatile memory, and it'll save it into a .mem file format. And there's a very important note here that I want you to have a look at, which is while performing the acquisition, an investigator must be aware of the fact that working on a live system may alter the contents of RAM. Why? Because in order for you to run a program on the live system, it has to be loaded into RAM. So therefore, you alter the contents, right? So any involuntary action performed on the systems may potentially make the systems inaccessible. So you actually might mess up the system in doing this. So you have to be very careful of running these volatile acquisition tools. Step number 5, we want to enable write protection on the media. We want to make sure that we block media from being overwritten. So right here, see this, there's a disk right here. You can see just the fingers of the person holding that disk with gloves on and writing information on about the model or whatever. And then right down here, we have areas that we can interface with the disk. And this is where we're going to be looking, what we're going to be looking at in some cases for making that read only on that specific drive. So we want to protect that data. So we can use what's called a write blocker. It's a hardware device, or sometimes when you can't do that, you can use a software application that allows data acquisition, but without but altering any of the contents. So it blocks write commands, a read-only access. So if it's a hardware write blocker, we install it on the device. We can boot the system with the examiner-controlled operating system. So examples of hardware would be CRU, WeProtect, or also USB write blocker or Tableau forensic bridges. And there are others, right? So this is on the hardware side. On the software side, we boot the system with the examiner-controlled operating system, activate write protection with SafeBlock or Mac Forensics Lab write controller, or there are many other pieces of software. So either way, you want to preserve every 1 and 0 on that original, making sure that it cannot be written to. Step number 6. With step number 6, we want to acquire the non-volatile data. So now that we've acquired the volatile data, we've turned off the system, we have write blocked the original, and now we can acquire that data from the hard disk. So there's no significant difference in the amount of data from a hard disk between live and dead acquisition methods, because it should be the exact same stuff. So with live acquisition, the hard disk, we use remote acquisition tools like even Netcat or bootable CDs, USBs. Kane is one. Dead acquisition, and we're going to remove the hard disk from the drive, connect it to a workstation, right block the disk, and then run the collection tool. So that's how it works. And in step 6, some of the tools that we might be able to use is here's a Windows Forensic Workstation, and this is dead acquisition. We could use Access Data FTK Imager, for instance, to acquire that information. Let's zoom in here and have a look. So in this case, we're using Access Data FTK, and we are selecting the location for the image and giving it a file name and setting some of the other information about it. And now it's running. It looks like it's actually finished. It says it's been created successfully. And if you look a little bit higher here, you'll see the MD5 and the SHA-1 hash for making sure that both images, the original and the image, match 100%. So that's FTK Imager. And now that brings us to step number 7, planning for contingency. So there are contingencies, like for instance, the hardware does not work. The software doesn't work. You are attempting to get that data, but you have a failure that occurs during the acquisition of that data. So we're going to look at several areas here. Number 1 is hard disk data acquisition. And so you want, as an investigator, to create at least 2 images of the digital evidence to preserve it. 1 copy, if one of them becomes corrupt, then you can use the other, right? What we like to say is 2 is 1, 1 is none. 2 is 1, 1 is none. So if you have 2 copies, that's great. 1 goes away, oops, you still have the copy, right? So, and now you have 1. So at least 2 copies. And then we're going to we're going to use imaging tools. So if you have more than 1 imaging tool, like for instance, you have Pro Discover Forensics, or you have Access Data FTK, it's recommended to create the first image with 1 tool and the second image with the other tool. So if you have only 1 tool, then you want to make 2 or more images with the same tool. And that gives you extra coverage from that other tool. So we want to use both tools to make 2 copies, or in this case, we're going to use 2 copies with the same tool. Also, we need to look at hardware acquisition in terms of contingency in step 7. So we want to use a hardware acquisition tool like UFED Ultimate or IM Solo 4G3 IT Ruggedized. What does it do? This actually can access the drive at the BIOS level and copy data in the HPA, the host protected area. This is very nice to have very low level cloning, copying of that drive. What about encrypted drive? So you have a drive that's been encrypted by the user, and you need to be prepared to deal with encrypted drives that use user-provided, and you'll need to use the user-provided decryption key for decrypting. So for instance, Microsoft includes the full disk encryption feature, which a lot of people use. You might be using it. I've used it many times, called BitLocker. And you'll find that on virtually every Windows installation that you find. But BitLocker is available on those. It's not always used, but if it's used, you'll need to go find and acquire the decryption key. Step number 8, we need to validate the data acquisition. We want to make sure that it is 100% valid. And so we want to calculate the hash value. We saw that a little bit before. That unique number is going to be our digital fingerprint, 100% unique. Some of the hashing algorithms, CRC, which is a cyclic redundancy check, MD5, SHA-1, SHA-256. Anyway, we want to choose the algorithm or algorithms that we're going to use to validate that data and make sure that not 1, 0, or 1 has disappeared from the original to the copy. When we're doing that in step number 8, there are some utilities that we can use to do this. Number 1, in good old PowerShell is get file hash. It's just a look at the commandlet, get-file hash, and then the path, and then you see that little vertical line. And the second line, that's a pipe. We pipe up to a format list, which is just a way of displaying the hash. So you see there's an MD5 hash, and just go ahead and memorize that hash real quick. No, you don't have to memorize it, but you need to make sure that it's the same in the original as in the other one. So get-file hash commandlet is one that you can use right there in Windows using PowerShell, and you want to also use commercial versions of this in your commercial forensics programs that have built-in hashing. So ProDiscovers, it's a .eve file, has metadata in segmented file acquisition files that have the hash file of the original. If you load ProDiscover, it compares those values. If they don't match, then you get an alert and tells you that it's not reliable. All right, so here's another note. It's always good to look at notes because they have important intel for you. And in most computer forensic tools, raw format images do not contain metadata. For raw acquisitions, therefore, a separate manual validation is required. So going back to what we were talking about raw acquisitions, you need to go back through and do an analysis. All right, so in this module, we've looked at data acquisition and the types of acquisition and some of the formats for that data acquisition. And then we spent a little bit of time looking at the data acquisition methodology. And so that's what we have for this module. In the next module, we're going to be looking at what an attacker is going to try to do to stop you from collecting all this information and tracking them down. And that's called anti-forensics. Join me for the next module.